everyone! Welcome to part 2 of chapter 19. Today we're going to continue our talk on electrochemistry. So last time we looked at redox reactions, and we said that redox reactions had a transfer of electrons, and we could use that transfer of electrons to generate electricity. When we were able to tell whether something was being oxidized or reduced based on its change in oxidation numbers, which told us, whether it had essentially gained or lost electrons. So today we are going to take that knowledge that we've learned and we are going to apply it to the creation of electrochemical cells and talk about how we can use those cells to generate electricity. So first we need to talk about electrical current. So if we think about a stream, right, a stream flowing through the woods, when we talk about the current, we're looking at the amount of water that passes by a given point in a given period of time. This is the same way that we will look at electric current. We're going to look at the amount of electrical charge that passes a point in a given period of time. So this can be electrons that are flowing through a wire, it can be ions that are flowing through a solution, but we're looking at a flow of electrons. Okay, and if you look at my diagram, we're going to see this diagram a lot today. Our electrons, because they are negatively charged, are always going to flow from somewhere that it's negatively charged. We're going to call this the anode, and it's going to flow towards a positively charged cathode because the electrons are negatively charged and they are attracted to a positively charged side. This is going to be our electrode. Okay. When we have a solution, right, say copper sulfate, we have copper 2+, and then we stick a piece of zinc in it, we can have a flow of electrons from the zinc to the copper. Okay, so our zinc over time will go from Zn, right, just neutral Zn, which has a 0 oxidation number, to zinc 2+, which would have a +2, right? So zinc would lose 2 electrons, and those electrons will go to the copper. Copper will go from a +2 to a 0, which means it will gain 2 electrons. So all of the electrons that are being lost by the zinc are going to be gained by the copper. So we could do this reaction in one beaker, but we're not able to capture that flow of electrons. And the only way we can do that is by separating the process of oxidation from the process of reduction so that we can use that flow of electrons to generate electricity. Okay, so like we talked about last time, redox reactions involve the transfer of electrons from one substance to another. So redox reactions have the potential to generate an electric current because we have flowing electrons. And like I said, to use that current, we need to separate the oxidation and reduction places. Okay, so they're going to, instead of occurring just in this one beaker, like in this example, we'll have them occurring in 2 separate beakers and be connected by a wire. Okay, so before we get into that, let's talk a little bit about electrochemistry in general. So electrochemistry is just the study of redox reactions that either produce or require an electric current. If we are producing an electric current, then we're going to call that a voltaic cell, right? And that's going to be spontaneous. But sometimes we can require an electric current and we can make a non-spontaneous cell, and we'll look at those. Those are called electrolytic cells. But more on that a little bit later. So the conversion between chemical energy and electrical energy is carried out in an electrochemical cells. And these are typically just going to be beakers for our chemistry purposes. Like I said, spontaneous redox reactions are going to take place in a voltaic cell. Sometimes these are also called galvanic cells, so you may see it written either way. In fact, I think Alex calls them galvanic cells. So just as a heads up, when you see galvanic cells, that's going to be the same thing as a voltaic cell. They both mean you're having a spontaneous redox reaction. And in these spontaneous redox reactions, electrons are being transferred and energy is being released. If we have a non-spontaneous redox reaction, we can make it occur. We have to input energy rather than in a voltaic cell, we are getting out energy. But in an electrolytic cell, we have to input energy to cause this non-spontaneous reaction to occur. So when we have these oxidation and reduction half reactions that we are separating, we call them half cells. So each oxidation and reduction, right? Each reaction will take place in a separate beaker. So we call them half cells because each one contains half of the reaction. And the electrons will flow along a wire that's going to be connected between those 2 beakers, between those 2 solutions. And that's where our electric current will flow. we need to have a conductive solid electrode in each one to allow the transfer of electrons to go through that external circuit, right? We're not going to stick our wire just in the solution. We're going to have our wire connected to a piece of solid metal, typically. Sometimes it can be graphite, but usually it's going to be a piece of metal. So you're going to have metal, sticking in a solution in a beaker, essentially with a wire connected from each metal. And then that wire and that electrode will allow the electrons to enter or leave the half cell. So the electrons can either go into the solution or leave the solution. And we have this flow of electrons, but we need to complete the circuit, right? So if you have taken physics, you always have to have a complete circuit. And if we didn't have a way, if we only had one wire going across, the electrons essentially would build up on one side and they wouldn't have a way to get back. And so we're going to have an ion exchange between the two half cells, and this is going to be a salt bridge, and that will allow the reaction to continue, okay? And that salt bridge will be made up of a strong electrolyte. So a picture, I think, would help us. Let's go hang on. Let's go look at a picture real quick, and then we'll come back to this. So here's a picture. So this is what I've been talking about. We have our, one of our beaker over here. We have another beaker over here. We have two solid electrodes up here, okay? And then they're being connected by a wire, which is up here, right? All of this wire. And then we would need to complete the circuit. So here is our salt bridge across the middle, okay? So you can see that the electrons could flow in a continuous circuit, right? You could think about it that way. Our charges can flow in a circle, which allows this to be essentially a battery, okay? Let's go talk more about this now. So we have two different electrodes, two different pieces of metals. One of them we're going to call the anode, and that will be the electrode where oxidation always occurs, okay? Oxidation occurs at the anode. I like to remember that because they both start with a vowel, right? Anode, oxidation, both start with a vowel, therefore they go together. This will be the more negatively charged electrode in our voltaic cell. And then we also have a cathode, and that's where the reduction will occur, okay? And that will be more positively charged. So again, these both start with a consonant, so I like to remember it that way. You can remember that the cathode is positive because the T kind of looks like a plus sign. So that would be how I would remember that. The salt bridge you saw going across the middle, we'll come back to that picture. It's going to be kind of a U-shaped tube, and half of it is going to be stuck in each beaker, essentially. And it will contain a strong electrolyte. So this will be an ionic compound that dissociates easily, so like sodium nitrate. And that will connect the two half cells. And essentially what happens is the ions in that salt bridge will act as counter ions to the flowing electrons, right? So the electrons are always going to flow from the anode to the cathode, essentially. They're going to kind of go like this. And if they just kept flowing that direction, then we would end up with a lot of, negatively charged ions, right, on one side and, not on the other. And we'd have a charge off balance, essentially. And so what we do is we have a salt bridge that goes across the middle and allows that charges to balance out. Okay, so the negatively charged ions in the salt bridge will flow to balance the accumulation of the positive charge at the anode. Okay, so we're going to have a bunch of our anions will end up over here, okay, because remember, our electrons are flowing this way. And so over time, our anode would become positively charged because it's losing electrons. So what happens is our anions flow this direction in order to balance the charge because our anions are negative, right? And we would have a positive charge over here, we kind of balance out. And then we have all of our negative ions that are traveling toward the cathode over here, right? This would be our cathode. And over time, our cathode would become really negatively charged. And so our cations will travel this way in the salt bridge so that they can balance out that charge, right? Because our cations are positive, our electrons are negative, and that will kind of balance out. Okay, and let me include that this is the anode over here. Okay, so that's essentially what's happening with that salt bridge. It's used to complete the circuit and allow our electrons to keep flowing. All right, so we were just talking anode, the electrode where oxidation occurs. Cathode is where the reduction occurs. One way you could remember this is you could remember red cat. which is reduction at the cathode, and then you would just remember that oxidation happens at the anode. Like I said, I like my little, vowels and consonants. That's how I always remembered it, but you might like to remember red cat. So I like to show off a bunch of different ways. All right, back to this. So here is our cell. Again, the oxidation is going to occur at the anode, and the reduction will occur at the cathode. Just by convention, we will typically show for a voltaic cell, right, one that happens spontaneously, we will usually put the anode on the left and then the cathode on the right, okay? And so the electrons are always going to travel from left to right. They're always going to go from the anode to the cathode. You can remember that electrons are negatively charged, so they're traveling towards our cathode, which is positively charged, okay? You can see those charges here. So our electrons are traveling towards our cathode, and that's how I like to remember that. Okay, once even one little electron flows from the anode to the cathode, then the charges in each beaker wouldn't be balanced and the flow of electrons would stop. So that's the whole point of the salt bridge here, like I was talking about. The salt bridge is used to keep the charges balanced. All of the cations will move toward the cathode and the anions will move toward the anode to balance out those electrons, right? Because if we had one extra electron over here, we need one more sodium to balance out that charge. If we look at our cell, right, so I've kind of simplified it here. We have our zinc anode and our copper cathode. Well, over time, what's happening is our zinc is being oxidized, right? Our zinc is going to Zn2+. And over time, right, so our zinc is going to zinc 2+. And our copper, Cu2+, is being reduced. So it's going from copper 2+ to copper. So over time, our anode is going to dissolve, right? Because zinc is a solid metal, but our zinc 2+ is aqueous. So over time, as zinc is converted into zinc 2+, our anode starts to dissolve. The opposite is happening over at the cathode. Over time, our Cu2+ is gaining electrons and being converted into copper solid. So over time, our copper will actually grow. Our solid will start to look bigger, okay? So here we go. So over time, it's going to look like this. Our zinc would start to dissolve into our solution, and our copper would start to precipitate out, or plate out, as we call it. So over time, our anode will dissolve, and our cathode will grow, essentially, will plate out. Okay, so let's look at how to write the cell. So we have a shorthand representation of electrochemical cells because otherwise drawing this out all the time would be really cumbersome. So the way that we write this is we're always going to write our electrodes on the outside and our electrolytes on the inside. So our solids will go on the outside essentially, and our solutions will go on the inside. Okay, we're always going to write our oxidation on the left because in the picture, right, our oxidation half cell is going to be on the left and then the reduction half cell is going to be on the right, just like in the picture. We're going to separate the phases in our half cells by single lines. So here, our electrode is usually a solid and our electrolyte is aqueous. So we separate the phase of those by a single line. Okay, same over here. This is aqueous, this is solid, so we separate the phase by a single line. If we had multiple substances that were in the same phase, right, and that'll happen if we're maybe changing the oxidation state of our metal, then instead of putting that single line, we would put a comma. Okay. Usually what will happen is if we have a comma, then you'll also have an electrode that goes with it. This would be like an inert electrode, like platinum. We'll get into a little bit more of that in a little bit. And then we have our double line in the middle. That is going to be our salt bridge. Okay, and it's used to kind of look like a salt bridge. So that will be in the middle. We have our oxidation on the left, reduction on the right. As you can see right now, there are no concentrations. If we don't write concentrations, right, and obviously you won't write them for solids, but of our aqueous solutions, if we don't write that we have a concentration, then you're going to assume it's 1 molar. That would be standard conditions, and we're going to get more into standard and non-standard conditions a little later. But if we don't see a concentration, assume it's 1 molar. If it's not 1 molar, then you need to include the concentration. All right, so let's look at this. So here is our zinc and copper reaction that we've been looking at. So we have our zinc being oxidized on the left and our copper being reduced on the right. So the way that we would write this out is that we would have our zinc solid, right, which is our anode material, and then we're going to separate it by a single line, and then we have our zinc solution, right? And then that will take care of the left, and then we'll put our double line for our salt bridge, and then we have our cathode solution, and then our cathode material. Okay, remember, solids are always going to go on the outside, and then our solutions will go in the middle, separated by the salt bridge. Okay, so inert electrodes. So in this reaction right here, our electrodes, right, both our anode and our cathode were participating in the reaction, right? Our zinc was being converted to zinc 2+, and our copper 2+ was being converted to copper solid, right? So our anodes and our cathode are being part of the reaction. But sometimes we don't want our electrode to be part of the reaction, and that will be when we use an inert electrode. And so this would be if we have an oxidation or reduction of an ion to a different oxidation state, right? So if we're changing the oxidation state of our metal, we might want to use an inert electrode because we don't want it to participate in the reaction. We will also do that when we have an oxidation or reduction of a gas, and that will, just give a surface for the reaction to take place on, right? So that we can have that transfer of electrons, but it's not going to participate in the reaction. And so we often use platinum for this because platinum is pretty unreactive. So here's an example in which we're using the platinum electrode, right? So our inert electrode. Our half reaction on the right involves reducing our manganese from a +7 to our +2. So our manganese is going to essentially gain 5 electrons, and those are both aqueous ions, right? That's all happening in solution. So Mn2+ and MnO4-, we need a transfer of electrons between those two species, right? So neither one of those is a solid, so we can't use it as our cathode. So instead, we use our cathode as we have a platinum, and that's just where the electrons will gather, essentially. So we have somewhere for our electrons to go so that our reaction can happen on the surface of the platinum without reacting with our manganese or reacting with our permanganate. And like I said, platinum works really well. It's not reactive and conducts electricity really, really well. So when we write out the cell, nothing's different about our anode. We still have our solid and our aqueous solution. And then again, they're still separated by the salt bridge. But on the right, we have our reduction that's happening. So we're going from permanganate to manganese, right? So we have, this is going from a +7, my apologies, to a +2, and so that's being reduced. So we're still going to write it as, this is gaining 5 electrons, right? So we're putting the species that we are reducing on the left and our reduced species on the right here. So it's supposed to be permanganate and then manganese, not the other way around. Hydrogen is also going to be present just because it needs to be done in an acidic solution. So we're putting commas for all of those because they are all in the same phase. They are all in aqueous solution. And then we will have our single line to indicate that platinum is our cathode. Okay, since we don't have any concentrations, we're going to assume that all of these are 1 molar, and therefore it's being done under standard conditions. Okay, so let's talk about current. So current is the number of electrons that are flowing through a system per second. And so our unit for this is going to be amperes, or amps for short, right? And we abbreviate this as just the capital letter A. So 1 amp of current is going to be equal to 1 coulomb of charge flowing each second. And this will equate to 6.242 times 10 to the 18th electrons per second. That's a lot of electrons happening. And so we're going to use this to do conversions and calculate, how many electrons are flowing per, a given amount of, current. And so our electrode surface area dictates the number of electrons that can flow. If we have a larger surface area, that will allow for more flow of electrons, and a smaller surface area would be fewer. So we can relate our current to our voltage, right? And our voltage will be the difference in potential energy between the reactants and our products. Okay, and our unit here will be volts. Volts is 1 joule of energy per coulomb of charge, and we will write that usually as volts are equal to joules per coulomb. Okay, and again, we were just talking about that we could measure current in coulombs. Okay, so that's how they are related. And the amount of force that's pushing those electrons through the wire is called the electromotive force, or EMF. Okay, and we can think about EMF kind of by thinking about a waterfall. If you think about a waterfall in terms of physics, right, our water is always going to flow from a place of high potential energy to a place of low potential energy. And our electrons will do the same thing. They're always going to go from a place of high potential energy to a place of low potential energy. So our electrons are always going to go one way. Just like in a waterfall, right, our water only goes one way. You would think it was really weird if our water just started going straight up the waterfall, right? Spontaneously, just went right up the waterfall. That would be really, really weird. Same thing, our electrons do not flow from the cathode to the anode by themselves. That is not spontaneous. They will always go from the anode to the cathode one way only. So the difference in potential energy between the anode and the cathode in a voltaic cell is called the cell potential. Okay, and we're going to look at the cell potential with respect to how easy it is to reduce one thing or another. Okay, we're going to look at how easy it is to oxidize something at the anode or reduce something at the cathode. Okay, our cell potential is going to be under standard conditions. We're going to call it the standard EMF, or E naught of the cell. So this stands for our electromotive force. This tells us at standard conditions, which would be 25 degrees Celsius, 1 atm for gases, 1 molar concentration of solutions. And then the cell means that we have added together our oxidation and reduction. Okay, so our cell potential is just going to tell us the difference in energy, essentially, between our two half cells. Okay, so the half reaction with a stronger tendency to occur has a larger positive half cell potential. Okay, and so if we're looking at, which thing will be oxidized or which thing will be reduced, we're going to look at which has a larger value. Okay, and when the two half cells are connected, the electrons will flow so that the half reaction with a stronger tendency will occur. So here, if we had hydrogen and zinc, right, say we were dissolving our zinc in some acid is essentially what's happening. Our electrons are always going to flow from our zinc to our acid. Zinc is always going to be oxidized and our acid will be reduced. Okay. So let's look at this mathematically. Here are two different oxidation reactions. Okay, so, two different oxidation reactions. Zinc is going to zinc 2 plus, copper is going to copper 2 plus. And if we look at them, right, we look at their relative values, we see that zinc has a positive value of 0.76 and copper has a negative value of 0.34. When we are looking at E naught values, or E values in general, the positive value is going to be spontaneous. So here, our zinc is the one that will be oxidized because it has a stronger tendency to occur. It has a larger positive value. Okay, so zinc has a stronger tendency to oxidize than copper. So our zinc will be oxidized, and if these were reacting, right, if our zinc was being oxidized, that means our copper is being reduced. Okay, so if you look, our reduction reaction here is exactly the opposite. We've just flipped it around so that we get our reduction instead of our oxidation. And when we do this, we are going to flip this value. So this value here would be 0.34 instead of being negative 0.34 because we've just flipped our reaction. So here it is. Here's the reaction. It's what we've been talking about before. Sorry, I kind of wrote over it, but our zinc is being oxidized and our copper is being reduced. This is the reaction we've seen kind of throughout today's lecture. So since we have zinc being oxidized, that reaction will happen at the anode, and our copper reaction will happen at the cathode. So we can't measure the absolute tendency of a half reaction. We can't measure whether it's going to be, the value of the oxidation or the value of the reduction, but we can measure it relative to a different half reaction. So what we do is we take hydrogen and we use that as our standard reduction potential, okay? And we're looking at the reduction of H plus to H2. So hydrogen is going to gain an electron. It's going to go from a 1 plus to a 0, so it's being reduced under standard conditions. And we're going to say that that has a potential difference of 0 volts. Okay, and so we can look at everything else compared to this hydrogen and assign reduction potentials to it. This is called a standard hydrogen electrode, and it's abbreviated SHE. So if you see that SHE, they're not shouting "she" at you, they're talking about the standard hydrogen electron. Okay, and so it's the reduction of H plus to H2 using a platinum electrode because it's inert. So here we can measure our oxidation potential for zinc using hydrogen, okay? So our half cell over here, this is hydrogen. So hydrogen is being reduced, okay? And so we're going to assign that a value of 0, which means that all of the cell potential that we are seeing on this voltmeter is totally from the zinc because we're saying that hydrogen is 0. Okay, so all of that electricity essentially that's being created is being due to the flow of electrons from the zinc. Okay, so zinc therefore will have an oxidation potential of 0.76 volts. So the standard hydrogen reduction potential is going to be defined to be exactly 0 volts, like I said. And so we're going to compare all of our reduction and oxidation potentials to this hydrogen potential, okay? Again, under standard conditions. So if these half reactions have a strong tendency towards reduction, then they're going to have a positive value for our E0 reduction. If they have a stronger tendency towards oxidation than our hydrogen, then they will have a negative value for our E reduction. So we're always going to write them as reduction potentials, okay? And if you look in the back of the book, you'll see them all written as reduction potentials. And the reason we don't include them as oxidation potentials is because you could just write them the other way and make them negative, and therefore, it would be an oxidation potential. So we're always going to write them as reduction. So if they are more likely to be reduced than hydrogen, they'll have a positive value, and if they are less likely to be reduced than hydrogen, then they will have a negative value, okay? And for a half reaction, just in general, like I said, if you wanted it to be oxidation, you just take the negative value of the reduction. So this is an important equation down at the bottom. When we are solving for our cell potential, okay, it's always going to be the reduction potential plus the oxidation potential. Okay, and remember though, our oxidation potential is going to be the negative of the reduction potential for that reaction. Okay, so reduction plus oxidation will give us E0 of the cell. So let's look at these. So here we are. Our highest reduction potential is going to be fluorine. We know that fluorine is really electronegative. Fluorine really likes to gain electrons, right? And so it has a very, very large reduction potential. I mean, look, even compared to like the next highest one, it's a very large reduction potential. Okay, and again, this is because fluorine is really electronegative, tends to gain electrons really, really well. So if it has a strong tendency to be reduced, that makes it a very strong oxidizing agent. It would therefore be a really weak reducing agent, but it's a very, very strong oxidizing agent. And then if we look at the other side, right, lithium, right, if we look at lithium, lithium is not very electronegative. Lithium only has, that one valence electron. It likes to lose electrons. And so it, has a very low tendency to gain electrons. Therefore, it has a very low reduction potential. Okay, this would make it a really weak oxidizing agent because it really doesn't want to gain electrons. But it is a very strong reducing agent because it tends to give up electrons really well, and it will cause something else to gain them, essentially. It will cause something else to be reduced. Okay, calculating cell potential under standard conditions. So again, we're always going to do reduction plus oxidation, and we're going to add those up. if you think about when we were balancing those redox reactions, sometimes we needed to multiply our reaction by 2 or by 3 to get those electrons from one reaction to cancel out with the other so that we could add them together. If you need to do this though, if you need to balance these, if you need to multiply the half reactions in order to balance your equation, do not multiply the E naught values, okay? The E naught values are going to get added together just the way they are. You're not going to multiply them by 2, you're not going to multiply them by 3, you're not going to do anything to them. The only thing you can do to your E naught values is either make them positive or negative, and then add them together. You're never going to multiply them by a number, okay? And this is because the cell potential is based on the potential energy per unit of charge, and so we say it's an intensive property, which means it doesn't matter how much of the sample you have. So it doesn't matter if you have times 2, times 3, times whatever, right? It's always going to have that same value. Okay, so let's use this to calculate E naught of the cell for this reaction. So the first thing we need to do is to separate our reaction into oxidation and reduction half reactions. So if we look, the things that are happening, right, we have aluminum going to aluminum 3+. That means aluminum is being oxidized, okay? And so if aluminum is our oxidation reaction, then everything else is going to be our reduction reaction. You could go through and again, you could calculate the oxidation states of nitrogen and see that it's being reduced, but it was really easy to see that aluminum was being oxidized, so you can trust that nitrogen is being reduced because they always have to happen together, right? If something's being oxidized, the other thing has to be reduced. So our oxidation is happening at the anode, our reduction is happening at the cathode, just like we've talked about before. So we can look up our reduction potentials for each one of these. Now remember, they are written as reduction potentials, not as oxidation potentials. But here we're going to need the oxidation potential for our aluminum because it's being oxidized. So we're going to take the negative value when you look it up. Okay, so normally this would be negative 1.66 would be our reduction potential. So in order to make it an oxidation potential, we're going to take the negative of it, and that makes it positive. Okay, we can just look up the reduction potential of nitrate because nitrate's being reduced, so we can just look it up and write it down. And now to get the E naught of the cell, we're just going to add them together and get our value. All right, I want you to try one. So here we go. You have some reduction half potentials below. You won't need all of them. It's just, so you can reference it. And you need to calculate E naught of the cell. So figure out which one, which reaction is oxidation, which reaction is reduction, what does that mean for our E naught values, and how are you going to add them together to get E naught of the cell? So go ahead, pause here, try that out, and come back when you're ready. Okay, let's go over this. So here we go. So we have our iodine in both cases, right, is going to be either oxidized or reduced to I2. So it's easiest to see this one. So we see I minus is going from a -1 to a 0. That means it's losing an electron, therefore it's being oxidized. So that was the easiest one to see, so we can trust that our iodate then is being reduced. Okay, so we know that our iodide is going to be oxidized. Therefore, when we look up that reduction potential, we need to take the negative value of it. So normally it would be 0.54, so we're going to have it be negative 0.54. And then we can just find the reduction potential of our iodate, and then we can add them together to get the E naught of the cell. So you'll notice here I didn't go through and try and balance my redox reaction, which you may have done. And the reason I didn't is because it doesn't matter, right? It doesn't matter if I'm multiplying by 2 or I'm multiplying by 3 or multiplying by 5. It doesn't matter because it's not going to change our E naught values when we add them together. So you totally could have balanced this. That would be great, but you didn't have to. Okay, so a redox reaction will be spontaneous when there's a strong tendency for the oxidizing agent to be reduced and the reducing agent to be oxidized. And so what this means is that we have, if we look at our table, our standard reduction potential table, we need one of them to be reduced. That will be the one that is higher up on that table. It has a more positive value. And then the one that's lower on the table will be the one that will be oxidized. Okay, so again, if you're looking at that big table, the one that's higher on the table has a more positive value will be reduced. The one that's lower on the table or has a more negative value will be oxidized. Okay, so substances that are listed at the very top of the table, they tend to undergo reduction because it's a reduction potential, right? So if they have a large value, they will likely be reduced, which means they are really good oxidizing agents, like we saw fluorine. Substances that are listed near the bottom of the table are good at undergoing oxidation, therefore they are good reducing agents. So what we need though, if we just need one on the top, one on the bottom. If we have, one on the top and one on the bottom, the one on the top is written as reduction and the one below it is written as oxidation, then that will be spontaneous. But if the one below is written as a reduction and the one above it is written as an oxidation, then it will be non-spontaneous. And again, you can go through, if that was confusing, if you just go through and calculate E naught of the cell, we need E naught of the cell to be positive. So like here, if we have, as it's written on top, right? If we have zinc being oxidized, which means we will flip this. Okay, that will be 0.76, right? Because if you look, our zinc solid is on the left instead of being on the right, which shows us that we flipped it. Okay, so if our zinc is being oxidized and our copper is being reduced, right, just as it's written, then we'd have 0.76 plus 0.34, which will give us a positive value, which tells us that it is spontaneous. But if instead we had zinc be written as it is, zinc 2 plus, right, so that's negative 0.76, and then our copper reaction has now been flipped. So that would be plus a negative 0.34. That will give us a negative value, which tells us that is non-spontaneous. Okay, so if if this was confusing about the, on the top and the bottom, you can always look at it mathematically. And if E naught of the cell comes out positive, it's spontaneous. And if it comes out negative, then it's not spontaneous. So let's look at this one. This says predict whether the following reaction is spontaneous under standard conditions. So we have iron and magnesium, Mg2 plus, and then we're looking at Fe2 plus magnesium. So iron is being oxidized because it's lost electrons, and then magnesium is being reduced because it's gained. So if we look at our half reactions, right, and then we look up our relative positions of the reduction half reaction. So this would be if I looked at the table and saw where they were, okay? So as it's written, iron is going to be on top of magnesium. It's going to be higher up in the table, which means that iron is more likely to be reduced than magnesium is. So if we look at our reaction, right, in our reaction, magnesium is written as the reduction, but I just told you that iron is more likely to be reduced than magnesium. That means that our reaction is not spontaneous as it's written, but it is spontaneous in the reverse reaction because iron is more likely to be reduced than magnesium is. So our reaction is spontaneous in the reverse reaction, like I said, and so we could go through and sketch the cell and label the parts. So again, our oxidation is going to be of the magnesium reaction and our reduction is going to be of the iron reaction. So this is what it would look like. So we would have our oxidation occurring at the anode. So magnesium 2 plus would be changing into magnesium. Our electrons are going to flow from the anode to the cathode. Our iron would be going from Fe2 plus to iron solid, and that would be occurring at the cathode. And again, don't forget the salt bridge. Okay, the salt bridge is a really important part, and people tend to leave that out. So let's apply this. Figure out whether each of these reactions would be spontaneous as written or in the reverse direction. So we don't have any numbers here, so we can't calculate the E naught of the cell. But again, if it's higher up in this reduction potential table, then it is more likely to be reduced. So that means that that thing needs to be written as the reduction reaction. If it's lower in the table, then it's more likely to be oxidized, which means it needs to be written as oxidation. So go ahead, pause here, try these out, and come back when you're ready to see the answers. Okay, let's look at the first one. So in the first one, we have fluorine being reduced and iodine being oxidized. So fluorine is written as the reduction reaction, which is good because fluorine is at the very top. So fluorine needs to be written as reduction. Iodine is down here, so that means iodine will be oxidized because it's lower in the reduction potential table. So therefore, this will be spontaneous as written because fluorine is being reduced like it should be, iodine is being oxidized like it should be. So now let's look at magnesium and silver. So here's magnesium and here's silver. So in our problem, magnesium is being oxidized, right? It's going from magnesium solid to magnesium 2+, and silver is being reduced. So silver is being reduced, therefore it should be higher on the reduction potential table, and it is. So silver is higher than magnesium, so silver is being reduced, magnesium is being oxidized, just like it's written in this problem, therefore it's spontaneous as written. The next one has copper being reduced to copper solid, and then iodine is being oxidized to solid iodine. So if we look at this, right, we find here's copper, there it is, and here's iodine, okay? So in our reaction, copper is being reduced, so copper should be higher on the reduction potential table, but it's not. Copper is below iodine on the reduction potential table. Therefore, copper should be being oxidized if this was spontaneous. So this will be spontaneous in the reverse reaction. In the reverse direction. All right, last one. We have copper is being reduced to copper solid, and chromium is being oxidized to chromium 3+. So copper is being reduced, so we would want copper higher up than chromium. So here's copper, here's chromium. So again, copper is in fact higher, therefore copper should be being reduced just like it is, so therefore it's spontaneous as it's written. All right, let's try another one. This is a good one. So this says, which of the following materials can be used to oxidize copper without oxidizing silver? So we're going to look for something that will only oxidize copper, not silver. So go ahead, pause here. Think about that one. Come back when you're ready to see the answer. All right, so let's go over this. So if we look, so we have silver here and copper, and so I think this one is actually pretty easy to figure out that it's got to be something to do with iodine, right? So it's not going to be fluoride, it's not going to be chromium because iodine is the one that falls in the middle, right? So if it's something, it's something to do with, copper but not silver, then it's got to be between there. So now you need to figure out, okay, well, is it the I- or is it the I2? So remember, we need these to be oxidized, okay, which means that we need our reduction reaction, okay? So we need it to be written as a reduction because both of these will be written the opposite way. We would write them as oxidation reactions instead of reduction reactions. So if we are going to write this one as a reduction reaction, then it's going to be as written. Therefore, this will be our reactant in our reaction. So that will be iodine is the answer, not iodide. All right. Here's a good problem. This is just to see how much you know about this lecture in general. Okay, so sketch and label a voltaic cell, which means it's going to be spontaneous, in which one half cell has silver in silver nitrate, and the other one has a platinum electrode in chromium nitrate, in chromium 2 nitrate and chromium 3 nitrate. So write the half reactions, write the overall reaction, determine the cell potential under standard conditions, do essentially everything you've learned so far. Make sure, to figure out which one is the anode and which one is the cathode. I haven't told you that, but if you look at the reduction potentials that you see below, you should be able to figure out which one is more likely to be oxidized and which one's more likely to be reduced. Start there before you start drawing things, and then come back when you're ready to see the answer. All right, let's go over this. So we had, let's go back to this. So we have silver and silver nitrate, okay? And then we have chromium 2+ to chromium 3+. So we're looking at silver and we're looking at our chromium reaction. Okay, so silver here has a larger reduction potential than our chromium reaction, which means that our silver is going to be the one that's being reduced and our chromium will be being oxidized. So that means that our chromium reaction will happen at the anode and our silver reaction will happen at the cathode. Okay, so remember, our anode is always going to be on the left and our cathode is going to be on the right. Remember, since we have both of our chromiums are going to be in solution, right, because they're both ions, we were using a platinum electrode. Okay, our electrons are always going to flow from the anode to the cathode, and don't forget to draw that salt bridge through the middle. Okay, our silver is going to be in our solution. We have our cathode being made of silver. And then you should have written your oxidation and reduction reactions. Remember, the way that they're written in that reduction potential table is always as a reduction reaction. So you need to flip the chromium reaction because we're writing it as oxidation, which means you also needed to flip the sign. In the table, this was negative 0.50 volts, so we flipped it. And then to get the overall reaction, we're just going to add these straight down. We didn't need to balance them or anything because we're just looking at the transfer of one electron in each. And then to get our E naught of our cell, we just added the cell potentials together. All right, last little bit, we can predict whether a metal will dissolve in acid using these reduction potential tables. So if we look at our reduction potential table and we look at hydrogen, right? We said hydrogen was 0. Anything that is below the reduction potential of hydrogen will dissolve in acids as a single displacement reaction. Okay, so like zinc is listed below our hydrogen on our reduction potential table. So that means that hydrogen will be reduced, which means that zinc can be oxidized. And when zinc is oxidized, right, our zinc metal is going from zinc to zinc 2+. And when it goes to zinc 2+, it dissolves in solution. So any of them that are below hydrogen on the reduction potential table can be dissolved in acid, which is a cool thing to know. But if you have anything that's listed above hydrogen on that table, then it's not going to dissolve in acid. Most things, though, will dissolve in nitric acid. So this would be, so when I was talking about acid before, just kind of like any acid really, but most metals will dissolve in nitric acid because we are having our nitrogen being reduced instead of our hydrogen. So that's a different reduction potential. And therefore, most of them now will fall below that reduction potential of nitrogen, and so it will be, we can cause them to be oxidized. If you were trying to dissolve, just as like a fun fact, either gold or platinum, they won't dissolve in regular old acids, they won't even dissolve in nitric acid. We actually have to dissolve them in a combination of nitric acid and hydrochloric acid. And this combination is called aqua regia. And so it's a noble water, right? And the reason we call it noble water is because it is one of the few things that can dissolve gold. All right, let's go ahead and try one. So which of the following metals will dissolve in acetic acid? So again, we're looking at the reduction potential compared to hydrogen, okay? And I want you to write the reaction for those that do dissolve. Obviously, you wouldn't write a reaction for those that don't. So go ahead, pause here, try that out, and come back when you're ready. All right, so again, if we look, so here's hydrogen. So hydrogen is always going to be reduced in these reactions because the way that we get our metal to dissolve is because it's going to be oxidized, right? Metals always lose electrons when they dissolve. Metals don't gain them. So metals have to be oxidized when they dissolve, which means that our hydrogen has to be reduced. So if our hydrogen has to be reduced, that means it has to be higher on the reduction potential table than our metal. So that means the only ones that can be dissolved in acid on this table are these three. So silver falls above it, copper falls above it, so neither one of those can dissolve in our acetic acid, but iron and chromium both can. So we can write reactions for both of those being oxidized to their ions. Okay, you could have written these as net ionic equations. That's totally fine. But again, when you write them as net ionic equations, just as a fun fact, remember that acetic acid is a weak acid, so we won't write this one as H+. We're still going to treat its reduction potential, though, as the same. And that's it for today. I know it was a bit of a long lecture. Thanks for sticking with it, but you learned a lot, right? We learned about how to create voltaic cells. That was kind of the sum of today's lecture. We looked at oxidation occurring at the anode, reduction occurring at the cathode. We looked at electrons flowing from one electrode to the other, and then we looked at that salt bridge, right, connecting through the middle. We talked about how to represent our cell using cell notation and how to calculate our E0 of the cell, right? We're going to use that table of standard reduction potentials, and we're going to use the reduction potential of the reduction reaction, and then we're going to add the negative value of the reduction potential of the oxidation reaction to get our E0 of the cell. If we get a positive value for the E0 of the cell, that would be a spontaneous cell or voltaic or galvanic cell. If we get a negative E0 of the cell, then that will be an electrolytic cell that we will talk more about in a later lecture. Lots and lots of stuff that we covered today. Please make sure that you are practicing these problems by completing the lecture worksheet problems. You have lots to do, but it's good to solidify these concepts in your brain. You'll be drawing some cells, you'll be calculating some cell potentials. It'll be great. As always, if you have any questions, please ask me so I can clear them up for you. We're going to use today's lecture as a foundation for more talks on electrochemistry, so really make sure you understand the concepts covered today. As always, if you have any questions, send them my way. I'm happy to help. Otherwise, I will talk to you guys next time.